All right, thank you for joining back for this afternoon. We have a few really great presentations left, including companies from Uptake, Tempest, and Innova. So we're focusing heavily on the data side of startups and the challenges within building data pipelines, working with machine learning, and more. So our next speaker is Dan Collins from Uptake, who's going to talk about data engineering the startup way. So please, a round of applause for Dan. The clicker.
Thank you. Hi, everybody. Hope you had a good lunch and have been enjoying the talk so far. As was said, I'm Dan Collins. I'm a senior principal engineer at Uptake, where I work on their platform for data engineering. So today I want to share with you data engineering the startup way. So to really give you the background, I need to tell you a little bit about Uptake first. And walk you through the problems that we solve, things that we have to deal with, the facts of life of data science and machine learning. And then I dive into more how we use AWS, how we continuously evolve, how we've grown as a startup, and then get into the meat of data engineering the startup way. So firstly, who is Uptake? Uptake was founded by Brad Keywell. He's our CEO. We have President Ganesh Bell. He was the first president of GE Digital. We're about 4 years old. We have about 100 customers. We've been named a CNBC Disruptor 50. We've been named a technology pioneer. We're one of the best places to work in Chicago by Fortune. And we're in the top 25 of Forbes Cloud 100. So we're definitely like later stage. And this graphic here will show you kind of our progression. So starting at the bottom in 2014, you can see big companies that we've worked with, as well as some of our accomplishments. To point out, we started with Caterpillar, working with predicting locomotive failure. So one of the things we point out there is $480 million of potential value in being able to predict when a locomotive breaks down and prevent those failures. We have really smart data scientists who are inventors, over 150 plus patent applications to them. We also work on wind farms, so $3.3 million in potential value from the work that we've done predicting turbine failure. We have 1.2 billion hours of machine learning data. We can deploy data science models in under 2 minutes, and we have 1,300 models deployed. So to get into it, I need to talk about solving hard problems. I'm sure all of you have really good ideas. That's why you're here. You're working on solving the problems that get your vision, your idea up and running. For us at Uptake, we're focused on industrial AI and IoT, which is really focused on predictive analytics, anomaly detection, label correction, applications in AI UX, as well as some preventative and prescriptive maintenance. So our main focus is really asset performance monitoring. So that means we look at all the sensor data coming off of equipment and bring that data in to do data science on it. So to jump into that, that means that we deal with industrial data. So lots of telematics data, lots of contextual data. So all the systems that have been around for years and years and years, SCADA systems, PLC and sensor data systems, we're integrating with these. Usually they're built for a different purpose. Usually they're built for maybe like a safety or near real-time monitoring, and we're pulling data out. And I'll talk about how we use AWS to bring that data into our systems to do data science on it. It also means we're interfacing with so much technology. So when you work with systems that are 30 years old, and then you also work with systems that were built, in AWS, you have integration points across all of them, and a lot of variety. Really, what we want to do is get data into our platform and insights out. But industrial data is really dirty, and by dirty I mean it arrives out of order. It's highly volatile. A lot of times we receive a system-wide snapshot, so it's like here's the 2 terabyte view of our data for the last hour. No deltas are in that data. So a lot of times we get data that's got predetermined aggregates. So someone 6, 7 years ago decided how to do sum, min, max, et cetera. They decided what the windows were. It's just locked in. You don't get to decide. Data is usually duplicated. Data is also partitioned, and data can be compressed in ways that you don't expect. Data has a past, so I mentioned this about systems being old. I also want to call out that when you're integrating with data systems over time, even as you've seen like companies starting in the cloud, the technology changes and you have to keep reevaluating. There are decisions and policy decisions in a company, like for example, hey, we didn't accommodate daylight savings time until 2011. So all our dates before that, you have to understand that they're UTC, but they're based in a certain time zone. Also, most integrations have a standard, but that standard doesn't live as long as the technology is evolving. So they're all following them, but the standards are all different. I should have had that slide with the XKCD. Let's fix the standards. It goes from 16 to 17 standards. So not only is the data dirty, we have different data integration. And I'll get into a little bit more meat here, but there's two primary ways. One is pull-based data integration, and one is push-based data integration. On the pull-based data integration, we're typically working with a client, and we're pulling data from a pre-aggregated source. So they might have a REST API. They might have an external broker. They might have a database that we can connect to. We might set up a VPN to pull that data out. And this is a lot of data. So telematics data, they talk about data in hertz. So you can get very easily into terabytes and petabytes. So when we reason about the data, we say, do we really need this volume of data? Like, do we need 60,000 readings every second to do the data science we're doing, or do we need some other grain? We also talk about normalizing that data as we bring it in, and I'll get there. The point here is there's a variety of mechanisms where we need to schedule and bring in or stream data from external systems of every variety, and they're usually pre-aggregated in a way that we have to learn about. On the push-based side, it's a little bit easier. So we can dictate a little bit. We'll say, these are the APIs we support. This is how we want to receive the data. There's lots of good integration services out there, AWS included, to normalize that process and make it easy. So sometimes data gets bundled on their side. Sometimes they're just streaming record by record. So just to give you a little bit more of a taste of this, you might think that, let's say I have 3 tenants. You might think that this is how the data comes in. So the numbers I have on here, they represent the event time. So each block is an event at a particular time. And then on the bottom, I have like T1 through 10, which is the processing time, so when we receive the data. And you might think that we're scaling up to a nice, reasonable amount of 150,000 writes a second. But what this really looks like across tenants and integrations is something more like this. So in practice, the data is not only dirty, but it comes in sporadically. It's based on ETL scheduling and failures that might happen in external systems. We're quarantining it. We're validating it. We're making sure to persist intermediate updates. And we need to be consistent. And I'll talk about this. Because building a machine learning platform is much different than building any other type of data system. So when you're doing inferential statistics, it's just it's good enough to say, I have a snapshot of the data, and I can go analyze that data. For data science, you're training models that are based on that snapshot, and you have to be consistent as you stream in the data from both training and scoring side. So as you notice here, maybe my first tenant on this platform sends me records, and there are kind of gaps in the records. Maybe I'm missing record number 4. Second tenant sends me a batch, and then they're quiet for a while, and then they send me other records, and then they're duplicated. And the last tenant is sending me record number 1 over and over and over again. So there are questions here that come up all the time, like, do you take the first one? Do you normalize it and take an average of those, values? Is it the last one that's the actual fact from what the reading was? So all of those things come to play. So at a high level, this is the system that we've built. It looks more like a Lambda architecture, but it's got some subtle differences. We bring in data, and we do ingestion, so this reads from left to right. But first of all, we have IoT devices at the edge. So this might be we are integrating with a third-party vendor that has devices on these big assets. We might be integrating with a pre-aggregated data source. We do have like edge and IoT capability, so we push data science down to the edge device to do not only like prediction at the edge and insights out there, but also just sampling for us so they can downsample the data before it comes in. Once it comes into our platform, we have an online streaming, which does all the real-time scoring. So this is where those 1,300 models are running, looking at data coming in the platform, making predictions. And then we have our batch layer, which is aggregating all the data so we can build models on top of it. On the right-hand side is where we get our applications. So lots of machinery. It's like the iceberg. Underneath the covers, there's a ton of stuff going on. And on top of it, you'll see a nice dashboard that allows you to easily navigate through. Here are the assets I'm looking at. Here are the predictions that came through. Based on these patterns, this is what I'm seeing. So yeah. So the first time you build this platform, like you've done the data science locally, you've got a model that's working against some sample data maybe. You build up the platform and you build your MVP and you say, we did it, we got it. The platform's there. And then someone comes along and they say, how else could we use this? And we signed a new client and we have a new tenant or we have a new use case with an existing client. And you say, well, it's pretty easy. AWS gave us all those tools to stand it up again. So I have Terraform. I know how to do this. So copy paste. I have a new instance. And then copy paste. I have another instance. And I can't remember who it was. They were talking about a little bit of a configuration drift, maybe with Chef. But over time, as you build out, you get lots of instances of platform, and every client will have custom service work that comes in, and it becomes very difficult to keep these all in sync. So, oh my. Where we've kind of evolved to, and I'll talk about this, is you need to start thinking about your platform as that shared foundation. And for us, I think about it kind of like if you've ever played with Legos, you get a base plate. That's where you start. However, when I'm thinking about like AWS is the base plate and a bucket of Legos that make you, 10 times faster building up your platform. And then on top of that shared platform, you can jump into configuring new products, building your own solutions, extending features on top of it, and we'll get into there. But I kept talking about variance. I talked to you about a little bit of the solving the problems and the things that we see with data integration. So I really want to get into facts of life. So with data science particularly, I hear this all the time. So there's a paper that was published in 2014. It's called Machine Learning, the High Interest Credit Card of Technical Debt. And it really calls out how difficult it is to build these systems. So this was one of their main takeaways. They talk about, when you're building an ML system, everyone wants to talk about the machine learning code and the neural nets and all the cool things you can do. And we keep, finding new ways to make this accelerated. But the hardest part is all the supporting configuration, data collection, monitoring, resource management. And this is where we spend almost all of our time. So if you ask any data scientist, most of the time they'll say 80% of our work is just trying to get data into a format we can use. And that brings the next point. So the second point in the paper they make is this concept of case. Changing anything means you've just changed everything. So if you change a validation method, you change your quarantine pattern, you all of a sudden are able to process data a little bit faster than you were before. You change how it's partitioned. You change how frequency of a particular piece of data comes in. All of that impacts your models. So there's a lot more that goes along with that, but the kicker here is when it fails silently. So you have a machine learning model that's running. It's looking for anomalous behavior, and you don't realize that it's drifted. So to recap our facts of life in solving hard problems, you take really dirty data from really old systems, you scale them up 150,000 writes a second, You spin up data science models on top of them and balance them very carefully. What could go wrong? And I put this out here too, the XKCD with the machine learning system, a pile of linear algebra and stirring it to get the right answer. Anyways. So to make all this work and to get to where we are today, we had to continually evolve. And so I really want to tell you a little bit about what we've learned, as well as ways that we're using AWS to do what we do. So when I think about continuous evolution as a startup doing data engineering, I think about these 4 things. I think about doing proofs of concept, or MVPs, not being afraid to take a risk on to learn quickly that you're going to fail. I fully commit to building those proof of concepts, so when they do show promise, you should let them go a little bit farther and actually get them up and running at scale. And then you need to learn from that, and you have to keep doing that process over and over and over again. As was said earlier with the comparison of like the AWS startup in 2010 versus 2018, it's also important at every end of that loop, you take a look around. What has changed? What things could I maybe use to remove the noise? So when I think about proof of concepts, I think about prototypes. For us, this really comes from, we have data scientists who get samples of data from an assessment. You might get a spreadsheet that's just this gigantic thing, which is a snapshot of data. And they'll get it working in R and Python. And then they might say, we don't really have the local memory to process all this data, so let's spin up some Amazon environment and bring up a really beefy box, some i3 or huge box that allows you to do testing on that data set to prove out the concept you're trying to solve. This is also where you might Dockerize it, you make it repeatable, and you're just focusing on the problem and trying to prove out if it actually works. AWS definitely unlocks all of this. So you have your low-touch, ECS Fargate. You can just go deploy. It can run against Kinesis. But you also can go and work with like EC2 and customize to your heart's content. Building it out is really about you've got something working, and you've got the prototype up and running. Now it's time to like actually put real data against it. This is also about scaling it out. When you're first doing something, you do it, and then you have to do it right, and then you should do it better. This is about figuring out whether or not you're doing it right. Does it scale the way you want? Definitely lean on managed services. I think one of the coolest things here is if you're using any like regular relational data store or NoSQL data store, you can go in AWS, and with a few clicks, you have that up and running. You can pump data into it for all your kind of environment prep. But then you can actually take existing production or staging data and run it through your data science. You can also be very production ready very quickly because you have all these established patterns to work on that are built for scaling out. So I showed you the diagram before, of the hard parts of machine learning and building a system that does predictive analytics. AWS really kickstarts your data engineering in all these different places. It gives you capability to do the serving infrastructure, monitoring, resource management, process management tools, data collection, as well as other things. And learning from it, this is really about taking the patterns that you learned. So I spun up an i3. It was really great until we split it out to 20 boxes, and now the cost is so high that I don't want to really run that at scale, so maybe I want to bring that back. Or there's a more efficient algorithm. What if we try that? You should go from bespoke. So, hey, they have this really cool idea. Let's see if it works. Oh, it worked. Let's bring that in, bake it in, make it codified so it's not you're repaying that for every additional kind of onboarding. You should always review your trade-offs. Remember, there's no right decision in software architecture. There's only trade-offs to be made. Analyze your compute, your I/O, parallelism. There are a ton of tools that you can use to do this. Definitely lean on the scientific method and all the AWS huge array of services. The The other thing is I feel like with having a cloud service behind you, it's kind of like being in a video game. Like you're just this little character who's running around, but you go in your inventory and it's like Walmart is there and you can like, go to the refrigerator section, eat something, AWS, I feel like every time I watch a reInvent or whatnot, I see new services that are launched. And I feel like that's how you should be as a startup. You should be open to looking at all the things that you can use so you can focus on your problem and not focus on things that are just readily available. So repeat. I'm going to quote Layman's Law of Software Evolution. I think this was initially part of a paper that was published in 1977. It's been iterated on since then, but essentially it says any program that is used and that as an implementation of its specification reflects some reality, it undergoes continual change or becomes progressively less useful. So that's to say, like, you are constantly iterating, taking in change, modifying, or you're becoming obsolete. The other thing that's pointed out here is that change process or decay process continues until it's cheaper to replace the whole thing than it is to just keep doing change or letting it decay. With Amazon in the mix, you can definitely go through this process faster before that change preempts you to recreate. But the other point here is that because they're good patterns and practices, you don't have to make all the trade-offs. It's not as much variety in my mind. So now you have all the context. I can go into data engineering the startup way, and I can tell you a little bit about more things that we've done, and maybe lessons learned you can learn from. So when Uptake started, we did definitely the proof of concept, get things up and running. And we had a monolith, really, a single application that made everything work. It did asset performance monitoring. It did data science. We proved the value. When the first time you predict a locomotive failure and they can then solve that, it's one of the coolest things ever. I wasn't at Uptake at that time, but I just feel like it's amazing every new industry that we go into. The other thing I'll call out is there's a YouTube video from Paul Denton on the ARC Orlando talk. He's from Progress Rail, and he talks about how the tools that we've built and have totally changed how they do failure prediction and maintenance. And he talks about how we have like 90% coverage of faults for locomotives. So in our evolution, that sticks out. We were a monolith. We were there, we were going fast, we were growing big. So we kind of split into microservices at that point. So the thought was we can decouple teams, we can have them focus on specific things. And this is where we kind of embraced Docker. At the time, ECS wasn't really an option, so we had our own orchestration in the back end. And Docker running data science, Docker running our applications, and really a platform that was based on that kind of same abstraction. So as we went, that worked well, and then I brought up the platform copy-paste problem. So you kind of get to platform, where you have to have that shared base, that shared foundation. And this is where it really comes in, I feel like. You can't start necessarily building platform because you don't know what your paved roads would be. You don't know what those patterns are. AWS out of the box gives you a lot of those patterns just codified for base infrastructure, for base kind of features and capabilities, but the thing you want to do isn't in there. You can't just hit a button and go. And your survival depends on that flexibility and feedback. So as you go through this loop, having tools to do that quicker and to take that feedback only help you. So I couldn't talk about data engineering the startup way without doing a quick plug on culture. I think if you're doing fast iteration and looking for flexibility, you also need engineers who are excited about doing this, and you also need a culture that embraces that kind of way of working. So we do things like hackathons. We have cross-functional teams, so we try to keep our QA, our DevOps, our SREs, and all development kind of together with product. That way we're all talking together. There's not kind of the toss it over the wall for implementation or toss it over the wall for operations. We do open source code nights. We also do like Friday maths. Maybe that's more a data science company thing, but Training and train the trainer are totally there too, so definitely make sure your engineers are getting the support they need, because I think being engaged means constantly learning. And the Albert Einstein quote, "Play is the highest form of research," and I totally agree with that. So these things here define data engineering the startup way to me. So first, focusing on your value. Second, choosing good abstractions. Third, acting like an enterprise. Fourth, investing. And fifth, being open. So first one, focus on value. You have great ideas. That's why you're here. That's why you've committed to doing startup-type things. But that also means that you have to be very clear about what you're doing. It means focusing on the problem that you want to solve versus letting other people solve the less interesting problems. So in the talks today, I've already heard a couple things where, hey, we were running our legacy infrastructure. It looked kind of like this. Could we pick up a new technology that gets rid of my management of EC2, or pick up a new capability with like Fargate, so I'm not even worried about my ECS deployments. You also have to use what's available when it's available. So like hindsight is always 20/20. You know, you'll look at your implementation, and it's always well, if we just had this other technology, it might have been easier. I think it's much better to have that like bias towards just acting and getting a decision, getting your build it phase going, and that's part of being a startup, and that's also part of data engineering the startup way. And really, this is just a call out. AWS lets you remove noise and lets you focus on where you're most innovative. Choosing good abstractions is a must. It means choosing ways to insulate yourself from hard dependencies. So like you want to take advantage of all these services, but you also don't want to get so tied to them that you can't change the implementation as you grow. So you don't want to also reinvent the wheel here. Like, don't introduce an abstraction just because you have to introduce an abstraction. But there are some really good patterns already out there you can just adopt, and it helps you. So one of those that's already been mentioned is like Docker, microservices. There's these patterns of developing software like test-driven development, continuous delivery, automation. And for the most part, these have been democratized. So if you look through the services that are out there, they have quick steps to get to that point. There's so many great tools out there that you just can't be afraid of change. You should embrace the fact that it's going to change and be ready for it. Act like an enterprise. So we were talking a little bit earlier today, and I kind of think it's interesting. Big enterprise software companies, they want to act like startups. So they're like, hey, how can we remove all the cruft and bureaucracy? We want to move fast. And there's this risk aversion as a big company you kind of have that holds you back. However, when you're a startup, you can do the opposite. You can look like an enterprise. You can work with enterprise clients because you're using world-class global services. So if I spin up something and I'm storing data in S3, I'm using EC2, I'm already working within a region of Amazon that has availability zones. I already have some of that HA figured out. I have solution architects who have looked at, hey, how do we deploy this in a way that's resilient? It makes your two-person team operate like an army of folks who can do infra and ops. It also makes your engineers that much more focused because they understand the abstractions that are already laid out for you. And so when you get questions about all those non-functionals of the systems you build, like your quality, your security, your scalability, all of those things, you can really point to the SLAs you already have from the services you're using. The other thing I'll point out here is when you act like an enterprise as a startup, you have to treat every outage just the same way. So use the tools to build services and systems that are resilient because an outage is an outage no matter how small. Your credibility as a company depends on your reliability and your ability to provide the services that you're rolling out. Invest is another piece that I think is super important for data engineering the startup way. It really means get really smart people and pair them with really great services to give you the flexibility to be curious. At Uptake, I feel like we have this great investment with the people that are working there, and we give them the tools that they need to go figure out new ways to do stuff. And it also means, because we've kind of democratized the way that we deploy, we have these standards in place, we're able to leverage AWS. We can also be curious. So what if we would have used XYZ service to do this? Or could we do a re-implementation and a POC of this capability? It also lets you put down a foundation in your data platform. So when you're evolving and you go, it's working, I have my monolith, I have my serverless architecture that's out there, but it's not scaling the way I want, and you're growing it, it allows you to think about, how do I make this the platform? How do I craft it? So investing in your data engineering gives you this repeatability, gives you this paved roads, and it really accelerates how quickly you're able to enable your client onboarding. I also want to talk about being open. So not only are there a lot of smart people you can have come work for you, there are a lot of cool projects out there that really smart people work on. Scala, Flink, Spark, Kafka, Postgres, Docker, Airflow, Kubernetes, Mesos, Kudu, Hive, Impala. The list could go on for pretty much ever. The thing that I will say here is when you find a problem, most of the time someone else has already looked at that problem in some way. And there are ways for you to get involved and give back. So odds are the thing that you need to work has some aspect of it that just helps the community at large. So if you go look out at our Uptake open source projects, you'll see some things in there from like our data science team, like our CRAN server. We also have a thing called PackageNet, which makes it easier to write our applications. And there's just good stuff about it. This goes back to that culture piece, which is take pride in your engineers and your engineer work, but also give back to the community. And you can do this even as a startup is the point. And it'll make you better as you grow. Last part is make sure to have fun. So when you're doing all of this, like, don't fight change. Don't get too overwhelmed with anxiety. Build systems that are flexible and organizations that are flexible. Use all this cool tech. Like, I feel like every reInvent, every time I get on any of the like tech news feeds, it's like, oh, they solved another problem I was thinking about a year ago. It's just really cool. I could never have imagined as like a kid who was taking apart a computer that I had like really begged for to be in a place now where I can just like think about having a computer and it appears somewhere and I can work with it. So there's never been a better time. Like, it's amazing. So recap, just to bring you back through the deck. So I talked a little bit about who Uptake is, all the stuff we're doing. I talked about why the problems that we're solving are hard and the things that make building machine learning at scale difficult, and the ways that AWS really takes care of a lot of the hard parts or that iceberg piece that you have to account for. I think also I talked about continuous evolution, so continually looking up, reevaluating the things that you take for granted, reevaluating the way you did it 3 years ago to see if there's a way that might accelerate your delivery. And it's really punctuated by your customer doesn't necessarily care about your infrastructure stack. They don't care about how well your deployments are working unless it impacts them. So lean on these things that come out that are new and make sure they're resilient and highly available so that they get the best possible experience. For us, that means making sure things don't fail. There's nothing better than saying, I'm predicting a main bearing failure on a turbine 300 days before it happens, and that client won't have an outage. So in summary, Uptake's awesome, I'm just going to say. And thank you for all the people on Twitch watching. I think Uptake's also watching right now, so hi, guys. There's hard problems, and we're solving them. You can solve your hard problems if you try. There's tons of tools in AWS that make it easier. Build, learn, repeat, and have fun. Thank you, guys.
Dan, thank you. I love the condensed amount of like best practice and advice to give. It's very, very helpful.
No problem.
Ben has a quick question, and he wants to know what does the training and scoring loop look like? So if the data is dirty and it changes frequently, how long before a model is no longer representative of reality?
So I can't talk too much in detail here, but I will say that when you bring in data to do your training on it, you will look at how to do your validation and how you do your quarantine on it. And that training scoring loop, I think, is something that you look at in practice. You also want to monitor it over time. As anyone who's launched a data science model would know, you can look at the efficacy of that model over time, in addition to looking at the efficacy of that model in comparison to like a newly trained version of itself. There's lots of platforms that do this too, where they like retrain and then compare.
And last question is, when you've got millions of dollars of wind turbines and locomotives on the line, how do you do controlled tests of predicting breakdowns? Do you let things break down to confirm your models?
Absolutely not. I think that would be the worst sales pitch, by the way. We're going to wait until stuff starts on fire, and then we'll take a look at the data. So this is a really cool thing, I think, where we're kind of like at the very edge of all the cool things we can do with data science and IoT. So I was reading, I think right now there's 11 billion IoT devices that are out in industry. So think about that, 11 billion things that are just sampling. It's the temperature right now. What is the temperature right now? And sending that data somewhere. And someone's looking at it and saying, the temperature between this time is X. We also have that data from your ERP systems. So somebody goes in to repair a locomotive. What happened when this locomotive blew up? What were the things that happened? Which wrench was used? We look at all of that data, we put it into context, and that's how we kind of correlate that data with the channel data. It's an amazing kind of thing. I can't really talk about how cool it is, but it's pretty darn cool.
But if you work there, you get the inside view
of
how it works.
Yeah, totally. Perfect. You could come check it out. You could even go bug the data scientists, even though I'm sure they'd love you for that.
Well, Dan, thank you very much. Really appreciate it.
Yeah, no problem. Thank you, guys.